Now we will solve some examples for static equilibrium. The first example is about the seesaw. A seesaw consisting of a uniform board. So we have a uniform board of mass capital M and length L, supports at rest. So we have static equilibrium. A father and daughter with masses m sub f, mass of the father, and m sub d, mass of the daughter, respectively, as shown in the figure. So the father is on the left, the daughter is on the right, they're sitting on this seesaw. The support, called the fulcrum, is under the center of the gravity of the board. So since this is a uniform board, and we have seen that center of gravity and center of mass locations are the same if we have a uniform gravitational acceleration, which is the case here. So the center of gravity will be right in the middle and the fulcrum is placed right underneath. The father is a distance d from the center, and the daughter is a distance L over 2 from the center. Part A, determine the magnitude of the upward force N exerted by the support on the board. Part B, determine where the father should sit to balance the system at rest. So you can see we identify all the forces here. The father feels the gravitational force from the earth, mass of the father times g. The daughter has a weight, mass of the daughter times g. Capital M times g that's the weight of the board, and the normal force exerted by the contact point. Okay, so we can place these forces here in this diagram. We have mf times g at a distance d from the support point, md times g at a distance L over 2 from the support point, and we have mg and the normal force here. And let's put our x-axis as the horizontal axis, y-axis, vertical axis, z-axis coming out of the page. Okay, so what is the condition for equilibrium? So the system is at rest. Therefore, for equilibrium, we must have the net external force y component to be 0. As you can see, these forces are on the same plane, so they're coplanar forces. So if I write the net force on the y-axis, I have the normal force pointing up, mg pointing down, mfg pointing down, mdg pointing down. So the normal force is in j-hat direction, and then I have mass of the father times g, weight of the father, pointing down, capital M times g, weight of the board, pointing down, and md times g, weight of the daughter, pointing down. So these should add up to 0. So this gives me basically a normal force N equal to the total mass, mass of the father plus mass of the daughter plus mass of the board equal to multiplied by g equal to N. So that's the normal force exerted by the support on the board, and it is basically in j-hat direction. It's pointing up. Okay, now where should the father sit? Since this is static equilibrium, the torque with respect to any rotation axis should be 0. So if I write Newton's second law rotational form and set it equal to 0, and let's do that with respect to the center of gravity location, our center of gravity. So if I write the torque, which forces will have a torque effect here? Because this is the pivot point I have chosen, these two forces will have no torque effect. Only the father and the daughter will have a torque effect. So from the pivot point to the application point of the force, I go, and then I see that the weight is pointing down. So using the right-hand rule, I see that the torque the father exerts is on the k-hat direction. So mass of the father times the gravitational acceleration times the perpendicular distance d in k hat direction. That's the torque due to the father. Now, what is the torque due to the daughter? The daughter is at a perpendicular distance L over 2, the weight pointing down, and I point my fingers from the pivot point to the application point of the force, curl them towards the force. The thumb points into the page, so I have minus mass of the daughter times g L over 2 k hat direction. So this adds up to 0. So I find that from this equation, the distance d the father should sit as measured from the center point is equal to mass of the daughter divided by mass of the father times L over 2. All right, so that's the answer I'm looking for. So I've obtained that using the rotational equilibrium condition. Now, we have seen that if the system is at rest, it's in static equilibrium, this torque equation should be satisfied for any choice of the axis of rotation. So that's what I'm going to check next. So just to make sure that I have done it correctly, this result should be independent of the choice of the rotation axis. Okay, so let's choose a different rotation axis. Let's try the daughter's location. The daughter position. Okay, so the reason I have chosen this as the rotation axis was because the two forces here do not contribute to the torque, and it makes my life easier in calculating the net effect. But if I choose the daughter's location, then the daughter's weight is basically pointing to the bottom at this location, so it won't have a torque effect at this point, but these three forces, normal force, mg and mf times g, will have a torque effect. So let's see. For the father, we have a perpendicular distance d plus L over 2 from this pivot point, and it's pointing down, the weight is pointing down. So using the right hand rule, once again I see that going from the pivot point to the application point of the force, curling my fingers towards the father's weight, pointing down, my thumb points out of the page. So I have in k hat direction mass of the father times g, the weight of the father, d plus L over 2, perpendicular distance, k hat is the torque due to the father. Now there's another force that points in the same direction as the weight of the father. That's the weight of the board that's in the applied on the center of gravity, basically. So the perpendicular distance is L over 2, so it will have the same torque effect, but the torque effect in the same direction. So I can say that the torque due to the weight of the board is plus capital mg, the weight of the board, L over 2, perpendicular distance, k hat. Now, how about the normal force? The normal force has also a distance L over 2, but it's pointing up. So going from the pivot point to the application point of the force pointing up, I see that the torque is in minus k hat direction. So minus n L over 2 k hat, this is equal to 0. Now what I'm going to do is basically substitute for n the result I have found from the translational equilibrium condition in part A. So let's do that. Mass of the father times g d plus L over 2, this remains, plus the weight of the board times L over 2, and minus, I have the normal force. The normal force is the total, is equal to the total weight. Mass of the father, mass of the daughter, plus capital M g L over 2. This should add up to 0. So that's what I have found in part A here. You can see that's the normal force. Now, so let's write this explicitly. Mass of the father times g times d, the first term, mass of the father times g times L over 2, the second term, plus capital M g L over 2. And then I have minus mass of the father g L over 2, minus mass of the daughter g L over 2, minus capital M g L over 2. This is equal to 0. So you can see that mass of the father g L over 2 terms will disappear, and also capital M g L over 2 terms will disappear. I will be left with exactly the same equation. So this will give me a result for D, mass of the daughter divided by mass of the father multiplied by L over 2. So I obtain exactly the same result with this choice of the axis of rotation. So this is the same result. So we have double checked our result using a different axis of rotation. Okay, so in this problem we have looked at the seesaw in equilibrium at rest when there is a father and daughter sitting on two opposing sides of the seesaw. The daughter is exactly at the end of the board, but the father is a distance d from the center. So from the static equilibrium translational equilibrium requirement, I have seen that the net force on the y-axis should be 0. So identifying the forces as the weight of the board pointing down, the weight of the father pointing down, the weight of the daughter pointing down, and the normal force pointing up here, I see that the normal force is balancing the total weight. So that was the answer to part A. In order to find where the father should sit to balance the system, I have looked at the torque with respect to the center of gravity, because there I don't have to consider the weight of the board and the normal force because they have no contribution to the torque. And the simplest possible torque equation I can write is with this choice. So that's what I have done. And I have seen that the torque due to the father and torque due to the daughter are in opposing directions, and that gives me D. Then I have double checked my answer by taking the torque with respect to the daughter location, where the daughter's weight is applied, and therefore it has no contribution on the torque, but these three forces have a contribution. And writing the torque due to these three forces and substituting for the normal force the total weight that I have obtained in part A, I obtain exactly the same result. So that checks. Now another example, standing on a horizontal beam. A uniform horizontal beam with a length of 8 meters. So first of all, this is a uniform horizontal beam. And a weight of 200 newtons is attached to a wall by a pin connection. Okay. Its far end is supported by a cable that makes an angle of 53 degrees with the beam as shown in the figure. So this figure is basically the figure at the right. And a person of weight 600 newtons stands a distance 2 meters from the wall. Find the tension in the cable as well as the magnitude and direction of the force exerted by the wall on the beam. Okay, so this person is standing right here. So there's the weight of the person pointing down. He's at a distance d from the pivot point here. The total length is L. It's a uniform beam, so it's going to have the center of gravity right in the middle and the weight of the beam pointing down here. There's a tension on the string and there will be a contact force here. Let's say that this contact force R makes an angle theta with respect to the horizontal. So the horizontal axis is the x-axis, vertical is y-axis, and z-axis is coming out of the page. The system is at static equilibrium. So basically, I will write the static equilibrium conditions. So the static equilibrium, remember, first requirement is translational equilibrium. So if I write the net force x components, they should add up to 0. So I see that R has an x component, R cosine theta. T has an x component, T cosine phi. So R cosine theta is in I hat direction, but T cosine phi is in minus I hat direction. So they add up to 0. The second equation would be for the y components of these forces. They should add up to 0. Now I have R sine theta pointing up, T sine phi pointing up, and these two weights pointing down. So I have R sine theta plus T sine phi, because they're in plus j hat direction, minus the weight of the person minus the weight of the beam should be equal to 0. And number 3, rotational equilibrium requirements. So let's take the rotation axis at the left end so that this contact force will have no contribution. So this is the pivot point I have chosen. The net external torque acting on the beam would be, so let's see here, this is the pivot point, this is the force WP pointing down, then I see that perpendicular distance d times WP in minus k hat direction will be the torque. So minus WP d k hat, this is due to the person. And similarly, due to the beam, I will have minus WB, the perpendicular distance is L over 2 k hat. Why is it in L over 2? Again, because the center of gravity is right in the middle. It's a uniform beam. And I have the tension contributing. The tension has a perpendicular component T sine phi. You can see here, that's the distance L, T sine phi pointing up, and the torque is in plus k hat direction. So T sine phi L plus k hat, this should be equal to 0. And this is basically written for a choice of rotation axis at the left end of the beam where it is touching the wall. Okay, so from these three equations, so from equation number 3, so what I was supposed to find is basically the tension, the magnitude of the tension in the cable, magnitude and direction of the force exerted by the wall on the beam. So this angle theta and R. So those three things I should find. From equation number 3, where R is eliminated because I have chosen this as my rotation axis, two of the unknowns are not present, only one unknown, tension, is present. So I can isolate tension from this equation, and it's going to be WP times D plus WB times L over 2 divided by L sine phi. So you can see from this equation, WP times D, WB times L over 2 would be on the right hand side, divided by L sine phi, I obtain the tension. That's basically the answer to the first question. All right, and this basically implies that because in the other two equations I will be dealing with T sine phi and T cosine phi, T sine phi should be replaced with WP D plus WB L over 2 divided by L. And if you see T cosine phi in an equation, that should be replaced with WP D plus WB L over 2 divided by L times cotangent phi, because I will have a cosine phi divided by sine phi, cotangent phi here. Okay, so let's go to equation number 1. Equation number 1 says r cosine theta must be equal to t cosine phi. So r cosine theta must be equal to t cosine phi. And equation number 2, the y components, r sine theta must be equal to wp plus wb minus t sine phi. So that is r sine theta equals to wp plus wb minus t sine phi. Now, if I divide equation number 2 by equation number 1, so 2 divided by 1 will give me tangent theta, sine theta divided by cosine theta, because I have r's cancelling, r sine theta over r cosine theta. So I eliminate one of the unknowns. So this gives me WP plus WB, weight of the person, weight of the beam, minus tension sine phi y component divided by tension cosine phi. So I can substitute for t sine phi and t cosine phi. Therefore, I obtain the angle theta as tangent inverse of WP plus WB minus, for t sine phi, I substitute this equation, WP D plus WB L over 2 multiplied by 1 over L. And for t cosine phi, I substitute this result, WP D plus WB L over 2 multiplied with cotangent phi over L. And you can see the 1 over L's will cancel here. So you will have basically just the parentheses remaining without the 1 over L's will not cancel because there's a WP plus WB. So that would be a mistake. Okay, so this is the answer basically. All right, so 1 over L's would cancel if this term were not present, but it is present, so we cannot cancel. Okay, so this is our final answer for theta. Now, what is r? Well, we can use equation number 1. R is t cosine phi divided by cosine theta. So this gives us for r, t cosine phi was WP D plus WB L over 2, and then we have cotangent phi divided by L. Now I also have cosine theta here, so L cosine theta. So for theta, I have to substitute this result. With that, I can obtain R. So let's do that here. R is equal to WP d plus wb L over 2 divided by L cotangent phi multiplied with 1 over cosine theta, which is 1 over cosine of tangent inverse this quantity WP plus WB minus WP D plus WB L over 2 1 over L divided by WP D plus WB L over 2 cotangent phi over L. Okay, so we have obtained the magnitude and direction of the force as well. So in this problem, we had a uniform horizontal beam where there's a person standing at a distance d from the left end, and because it's uniform, the center of gravity is in the middle. We have the weight of the beam. We have tension on the string pointing at an angle phi with respect to the horizontal axis to the left. And we have a constant, we have a force, contact force between the beam and the wall, and that is R. So we put an angle theta here with respect to the horizontal axis, which is to be determined. So the equilibrium condition we write by the net external force x component is 0, translational equilibrium first equation, that gives us r cosine theta minus t cosine phi, the only two forces that have a horizontal component. The net y component should be 0, r sine theta and t sine phi are pointing up, but the weights are pointing down. And as for the torque calculation, because I want to determine r, theta, and tension in this problem, and there are three unknowns, in order to eliminate two unknowns here, I have chosen this as the rotation axis so that r and theta will not appear in this torque equation. With that, the weight of the person, weight of the beam have a torque effect. One is at a distance d, the other one is at a distance L over 2, perpendicular distance. And t with basically the horizontal component will have no torque effect because it goes through the pivot point, but the vertical component t sine phi is at a distance L, perpendicular distance L, so t sine phi L will have a torque that is opposing the torque due to these two weights, and that equation gives us the tension in the string. And the t sine phi and t cosine phi we can write from this equation. And using equation number 1 and equation number 2, if we divide equation number 2 by 1, so we divide the y equation with the x equation, we obtain tangent theta. And by substituting for t sine phi and t cosine phi, using equation number 3, I can obtain the angle. And the magnitude is basically just t cosine phi divided by cosine theta. So for t cosine phi, I have this result. And for 1 over cosine theta, I will have 1 over cosine of tangent inverse this result.